Today we're going to look at section 2.2, which is compound statements. A compound statement is a statement formed by using a connective to join two independent clauses or logical statements. Excuse me. The joining of two logical statements with the word and, or but forms a compound statement called and or but forms a compound statement called a conjunction. In logic, for a conjunction to be true, all the independent statements that make it up must be true. Symbol for a conjunction is this kind of upside down looking V. Kind of looks like it almost an A. So that might help you remember A is and. Remember, with an and statement, all the independent logical statements that make it up must be true. The joining of two logical statements with the word or forms a compound statement called a disjunction. Using, unless otherwise specified, a disjunction is an inclusive or statement, which means the compound statement formed by joining two independent clauses with the word or will be true if at least one of the clauses is true. And the symbol for this disjunction is a symbol that looks kind of like a V, which is upside down of the symbol for and. So joining two logical statements with the word implies, or using the phrase if first statement then second statement is called conditional or implication. We use conditional. The clause associated with the if statement is called the hypothesis or antecedent, while the clause following the then statement or the word implies is called the conclusion or the consequent. Conditional statements notated with an arrow is like a one-way contract or promise. The only time the conditional statement is false is if the hypothesis is true and the conclusion is false. And the last one we have here, joining two logical statements with a connective phrase if and only if is called a biconditional. The connective phrase if and only if is represented by the symbol arrow going both ways. So here they are. Here are all our symbols. So we have and but, which is the upside down V looking thing, a conjunction, or, which is kind of V looking, which is a disjunction or inclusive, or not. We have the tilde for negation. If then implies conditional implication, and if and only if biconditional. So for each connective, write its name and associated symbol. So not, now this is negation, and it's simply the tilde. And this is a conjunction. And if and only if is biconditional. Translating compound statements to symbolic form. To translate a compound statement into symbolic form, we take the following steps. Identify and label all independent affirmative logical statements with a lowercase letter, such as P, Q, or R. Identify and label any negative logical statements with a lowercase letter preceded by a negation symbol. Replace the connective words with the symbols that represent them. A note, when translating English statements in the symbolic form, do not assume that every connective and means you're dealing with a compound statement. So if we let P represent the statement, last night it snowed, and Q represent the statement, today we go skiing, write the symbolic form of each of the following statements. Today we go skiing. That's Q, but last night it snowed. That's P. And the connective is but. So there we go. But and conjunction. Today we will go skiing. That is Q. If and only if it snowed last night, which is P. And we have if and only if, that's the biconditional. Then we have last night it snowed, which is Q. Today we'll go skiing. Nope, no, last night it snowed is P. Today we go skiing is Q. And it's an or. So there we go. If it snowed last night, then today we go skiing. So it snowed last night is P. Today we go skiing is Q. And it's an if then. So it's a conditional. There we are. Okay. So now comes the fun part. Translating compound statements in symbolic form with parentheses into words. When parentheses are written in a logical statement, they group a compound statement together, just like when calculating numerical or algebraic expressions. Any statements in parentheses should be treated as a single component of the expression. If multiple parentheses are present, work with the innermost parentheses first, just like in algebra. So we let P represent the statement, my roommates ordered pizza. Let Q represent the statement, I ordered wings. And let R be the statement, our friends came over to watch the game. So let's translate. So we start off with, we have an if then, and we have an or in here. So what this is telling me is I need to group this. So we'll start with if because it's conditional. If, and it's not are. So if our friends did not come over to watch the game, and the way we show the grouping in English, put a comma. So that's saying that's one thing, what's coming after the comma is the other. Then we have our then for the if then. And then we have P, my roommates, my roommates ordered pizza. And we have our or Q, I ordered orange. Isn't this so much more elegant? So what do we have here now? And we have in parentheses P and Q. And we have an if then statement represented by this and an and here. So we're going to have if P and Q. So if my roommates ordered pizza and I ordered wings. And again, we're going to separate that with the comma. Then our friends and over to watch the game. And our last statement is the negation of P or R. So we can start with something like this. It is not the case that my roommates ordered pizza. And again, we have or I ordered wings. You have to be careful. It's easy to get lost in here. Okay, as with algebraic expressions, there's a set of rules that must be applied to compound logical statements in order to evaluate them with consistent results. The set of rules is called the dominance of connectives. When evaluating compound logical statements, connectives are evaluated from least dominant to most dominant as follows. So it seems kind of backwards. You would think most dominant would be done first, but from least dominant to most dominant. And first we start with parentheses. Parentheses are the least dominant connective, so any expression inside parentheses must be evaluated first. Add as many parentheses as needed to any statement to specify the order to evaluate each connective. Next, we evaluate each connective, or next we evaluate negations. Then we evaluate conjunctions and disjunctions from left to right because they have equal dominance. After evaluating all conjunctions and disconjunctions, we evaluate the conditionals. And lastly, we evaluate the most dominant connective, the biconditional. If a statement includes multiple connectives or of equal dominance, then we will evaluate them from left to right. So for each of the following compound logical statements, add parentheses to indicate the order of operation or the order in which to evaluate the statement. Recall that parentheses are evaluated innermost first. So let's just rewrite this for now. Q and not R. So what are we looking at? Let's see. I don't have any parentheses. I'm going to put it. The first thing I'm going to do is evaluate negation. So I can signify that. So now I'm telling you, by my parentheses, do this first. Then we evaluate conjunctions. Now realize we're going to do P or Q before we do and not R. So we're like this. And then the whole thing. Okay? So next, again, let's just rewrite this. Not P, then Q or R. Okay, again, first up is the not P. Negations come before anything. Then we have conjunctions or disjointed or disjunctions. And then lastly, the if then conditional. This one's really messy. Let's see. Not P or not Q if and only if, and there's already a parentheses here. Oh, that's a not. So we're going to do these knots first. Then we're going to do this one. And that is it. And that finishes up section 3.2 or 2.2. Yeah, 2.2.